Welcome back, Chem 20s. We're going to jump in and look at the second way of measuring concentration. So the second way of measuring concentration is parts per million. Parts per million is the ratio of the mass of solute again to the mass of the solution. And then we're going to multiply that by a million. In grade 9, we looked at parts per million, parts per billion. Again, if we were doing parts per billion, we would multiply the end answer by 1 billion. But we're going to concentrate here on parts per million. We're going to look at masses for this. Again, it's going to be solute over solution. Smaller number is going to be on top. Again, when it comes looking at this, we honestly don't care what the unit is, grams, grams, milligrams, milligrams. As long as both mass units are the same, unit does not matter. Now, the thing that does matter, however, though, is typing this in the calculator correctly. If you don't know how to type in times 10 to the 6th exponent, then you could type in times 1 million. Just make sure you get the 6 zeros in there. Now, the interesting thing about why we use parts per million is because we use this for very, very, very tiny quantities. So a quantity that we might use this for is, let's say, the amount of mercury in water in the environment, or the amount of lead possibly in paint. Because we're dealing with such tiny, tiny values, we can actually assume that the mass of the solvent is actually equal to the mass of the solution. Because when you add the solute and the solvent together to get the solution, because it's going to be such tiny, tiny values, it's actually not going to change your answer at all. Now, this is very different than when we looked at percent by volume, where we had a liquid dissolved in a liquid, because those numbers are pretty close together. That would be an example, kind of like, hey, the vinegar in a solution, so 5% acetic acid in, let's say, water solution, or cleaning supplies, the percent of Mr. Clean inside, let's say, 2 liters of solution, or what some of us might understand as possibly the alcohol in a beverage, possibly when it says 6% alcohol in a solution. So for parts per million, we are actually looking at extremely minute, tiny little values. The other thing we have to look at is, because we are dealing with masses for water and for water only, we all know the density of water is 1 gram per, ideally, 1 milliliter. Therefore, 1 gram of water, and this is only true for water, equals 1 milliliter of water. So if I convert this, then that means that 1 kilogram of water actually equals 1 liter of water. Because, right, 1 milliliter is the same as 1 gram. So this would be 1, 2, 3, 1,000 liters. 1, 2, 3, 1,000 grams is the same as 1 kilogram. So these units kind of go together, and I'll remind us of that as we do a question. So again, like in the previous formula, we're going to do 3 examples. So example number 1, a 300-gram sample of tuna oil contains 5.4 times 10 to the 3 grams, times 10 to the negative 3 grams, much tinier number, of mercury. What is the concentration of mercury in the sample in parts per million? So over on the left-hand side, we're going to make our list. So we are trying to find parts per million. So we would like to find ppm. It tells me that I have a giant sample of, so this is going to be my solution, of 300.0 grams. It contains 5.4 times 10 to the negative 3, so that's going to be my mass of my solute. 5.4 times 10 to the negative 3 grams. Now, I look at this just briefly, grams, grams. I like this. Therefore, the units are the same. They'll cancel out. I can go over to my formula. ppm equals mass of solute over mass of solution. And you can again abbreviate times 10 to the 6 ppm. Now, When we substitute this in, grams is going to cancel. I put ppm here so I have a unit to know that this comes out in. Again, if you were to compare this formula to the textbook puts a C here for concentration equals. I like to put what we're solving for, so I like to put parts per million. So when we go to substitute in, solute, or the smaller number, goes on top. 5.4 times 10 to the negative 3 grams over 300 grams. And then, of course, we're going to multiply by 10 to the 6 ppm. So in my calculator, I'm going to type in 5.4 times 10 to the negative 3 divided by 300. Very small number. And then times by, and when I go to times by 10 to the 6th, if you want to times by 1 million, go ahead and do that. I like to go times and then second function comma to put the E on my calculator, the E that says, right, times 10 to the, and then I like to go 6. And on your calculator, if you typed it incorrectly, your answer will be in 2 sig digs, 18 parts per million. Again, grams cancel. So 1 mark for the formula, 1 mark for substitution with units, 1 mark for answer with units in the correct number of significant digits. Okay, let's try example number 2. For this example, why don't you copy it down, and over on the left-hand side, let's make a list of variables. This one's a little tougher, so if you're feeling confident, keep going. If not, unpause the video, check the left-hand side, then pause it again and keep going. So, example 2, if 10.13 grams of lead is dumped into 502 liters of water, what will the concentration of lead be in parts per million? So again, we are trying to find ppm. So we have a mass, so we're putting lead into water, so the solute is going to be the 2.13 grams of lead. The solution is 502.0 liters. Now, we know this value is 502,000 milliliters. And since 1 milliliter equals 1 gram, we know this is 502,000 grams. Now, they told us 1 liter equals 1 kilogram. So again, we could have done it that way. I think most of us, 1 milliliter equals 1 gram of water. So we easily changed to milliliters, then we changed to grams. So our formula, ppm equals mass of solute over mass of solution, got to fix that, times 10 to the 6 ppm. My mass of solute is 2.13 grams. My mass of solution is 502,000 grams, 10 to the 6 ppm. So 2.13 divided by 502,000 grams times 1 million. And my answer in 4 sig digs, 3 sig digs, so I'm going to have 3 sig digs, is 4.24 grams. Cancel. The only unit I have left is parts per million. Now, I want to pause for a second because we made an assumption in this question. So I'm going to change just pen colors for a second here. Grab something else. We'll grab pinkish. In this question, we made the assumption, right? We dumped it into water, 502 liters of water. Ideally, if we were really going to call this a solution, we would have added our 502,000 grams of water to the 2.13 grams of solute. And we would have had 502,002.13 grams. But remember, we made an assumption a couple slides ago, and the assumption we made was that the mass of solvent is going to be roughly equal to the mass of solution because the number is so small for the solute. So ideally, if you did this question again and you substituted instead 502,000 grams for the solution, this time you subbed in 502,000 and 2.13 grams, what you're going to see is you are still going to get this number. You actually don't run across a difference in this value until the third decimal place, the thousandth of a parts per million. Very, 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 very small. So you can use that assumption. Again, I would not mark it wrong if you added these two together, because ideally, if we were looking at this in perfect science, the mass of the solution would be those two numbers added together if you read the question and understood it correctly. Okay, last question. And again, I'm just going to use a pink pen for this question. When smoking, the concentration of carbon monoxide reaching your lungs is, so I know the parts per million, 198 parts per million. What mass of carbon monoxide gas would be present in a sample of air with a mass of, so my sample, my solution is going to be 9.6 grams. By the way, that is roughly what the mass of one breath in is naturally anyways, 9.6 grams. We would want to know in that how much of it is actually carbon monoxide. So we know it's going to be smaller than 9.6. So let's try this question. So we have ppm equals mass of solute over mass of solution times 10 to the 6 ppm. In this example, we're solving for mass of solute. So to get it by itself, mass of solution is going to multiply on the other side or move up. And it's the opposite of times 10 to the 6 is going to be divide by. So my moved formula is going to be mass of solute equals parts per million times mass of solution divided by 10 to the 6 ppm. So let's substitute this in. We have 198 parts per million. We're going to multiply by 9.6 grams. And then we're going to divide by 1 million or 10 to the 6 ppm. Notice my parts per million will cancel. The unit I'm going to get out in grams. So I'm going to type this in my calculator. 198 times 9.6, enter, divided by 1 million. And my answer is going to be very, very small, and it's going to be 0 decimal, and we are allowed 2 sig digs, it looks like, 0.0019 grams. So 2 sig digs, very small number. Again, marks for your original formula and the moved around one, marks for your substitution with units, and marks for your answer in units in correct sig digs. Again, if you wanted to put this in scientific notation, you could write 1.9 times 10 to the negative 3 grams, and that is also correct. This is how we do concentration for the first two types. This is percent volume in parts per million. Again, there will be a third video explaining molar concentration.